Good evening.
Good evening, sir.
Okay, so in last class, we have completed this thermal properties of matter. Next, we have to start with thermodynamics. This thermodynamics composed of two different words, therm, heat, dynamics, flow. So it is basically the study of flow of heat and conversion of heat from one form to some other form, like in mechanical energy, electrical energy, or some other form. So in this chapter, we mainly define flow of heat and its conversion in some different form of energy. The study of flow of heat and its conversion into other form of energy. So to start with this thermodynamics, let me define you some basic concept or basic term which will be used in this entire chapter. First is thermodynamical variable. These are the physical quantity such as number of moles, pressure, volume, temperature. May define the condition of gas at any instant of time. So you'll say those physical quantity on which the condition of gas may depend upon are called thermodynamical variable. The physical quantity which defines on which condition of gas may depend upon is called thermodynamical variable. So here we have N is number of moles, P is pressure, V is volume, and T is temperature.
So can you recap what you just started? I joined a bit late.
I've just started. Okay, Atif.
Okay.
Next is there will be relationship between these thermodynamical variable to define the condition of gas at any instant related to that expression, which is called equation of state. So equation of state is a relationship between those different thermodynamical variable to define condition of gas at any instant. The relationship between different thermodynamical variable which defines the condition of gas at any instant. So in general, or generalized form of equation of state will be Pv to the power x is constant, where x will be any numerical value, which may be represented as P to the power 1 by x V is equals to constant, or it will be PV equals to nRT as ideal gas equation. Is it clear till this part? Yusuf, any doubt?
Sir.
Okay, just write it down. You all have done?
Answer.
Yusuf, done?
Sir, last statement.
Okay.
Done, sir.
Now next will be molar specific heat constant, which I have already defined in last chapter. It is the amount of heat required to change temperature of 1 mole of gas by 1 degree Celsius or 1 Kelvin at given condition or at given process related to that gas. So it is the amount of heat is required to change temperature of 1 mole gas by 1 Kelvin or 1 degree centigrade at given condition. So it will be dq equals to n number of moles, C molar specific constant, dt change in temperature. Generalized formula for this molar specific constant C will be R divided by gamma minus 1 minus R by x minus 1. So x will be same, which is the exponential of V in the above part for equation of state. So try to find the value of x from the above part, put it here, you will get the value of molar specific constant related to that process. In this expression, we have R, which is called universal gas constant. So it will be equals to 8.314, but for calculation purpose, you may write 25 by 3 joule per mole per Kelvin. Atif, is it clear?
Yes, sir.
Now, the next part is gamma. To define this gamma, let me explain you. Degree of freedom. Degree of freedom simply states all the direction or coordinate in which gas may contain energy is called degree of freedom. Suppose, let me define you first about degree of freedom. The direction or coordinate along which a gaseous particle or molecule may contain energy. Suppose you have a monoatomic particle such as helium. So it will have ability to move along x-axis, y-axis, z-axis. Or you will say this monoatomic particle will tend to go along x-axis, y-axis, z-axis. So it will have translational kinetic energy along those axes. So it will have translational energy along x as well as y as well as z. So how many directions in which this monoatomic particle will contain energy? Atif,
Sorry, sir.
how many directions in which this monoatomic particle will move? So you'll say
Three directions.
Yeah. So it will have 3 different directions of energy containing, and all are translational. So we will say degree of freedom in this case will be 3 and all should be translational. Is it clear? Yusuf, any doubt?
No, sir.
Now suppose you have diatomic. Such as nitrogen molecule, oxygen, hydrogen, like this. First write it down till this part.
Sir, can you scroll up for a second? Thank you,
Furthermore,
sir.
okay.
Can you scroll down?
Yusuf, done?
The last point. Done.
Okay. Now let me define for this diatomic particle. So in this part, it will tend to move along x-axis as well as y-axis, z-axis translationally. So it will have three different translational energy or translational kinetic energy. This diatomic particle may rotate along this axis or this axis, but there will be no rotation possible along y-axis. Let me define you. Suppose this is your diatomic particle. So it may translate along this, or along this axis. So it will have three translational energy. It will have some rotational due to its rotation along this axis, x, z, but there will be no rotation possible along its own axis since it behaves as point object. So there will be no rotation possible along this way. So we can say in this part, it will have three translational energy and two rotational energy. So in total, it will have 5 different ways of energy containing. Atif, is it clear?
So can you explain once more?
Okay. In this part, suppose for diatomic molecule, H2, N2, O2, so on, which behave like any linear object like this. So this object may tend to go along x-axis to and fro, along y-axis forward and backward, or along z-axis upward and downward. So it may have three different translational energy due to its translational motion. Next, it may rotate along this axis, but there will be no rotation possible along this axis. Let me define you. If you see from this axis, which is along x-axis, so there will be rotation possible. If you see along this, so rotation will also possible, but along this axis, since it will behave as point object and for which there will be no rotation possible, okay? So they will have only 2 rotation and 3 translation. So in total, it will have 5 degrees of freedom. Is it clear now, Atif?
Yes, sir.
Okay. Anyone just tell me the structure of water molecule. Is it linear or something else?
Linear.
Linear.
So it's bent.
Good. Due to lone pair on oxygen. V-shaped like this. So if you have to calculate degree of freedom related to this part, so it may have translational motion along all degree of freedom, all different axes, x-axis, y-axis, and z-axis. It may move along this, this, and also it will have rotational along this axis, and along this axis also. So how many degrees of freedom it will have? 3 translational and 3 rotational. So in total, it will have 6 degrees of freedom. Atif, is it clear?
Yes, sir.
Riba, any doubt?
No, sir.
Okay, just write it down. Nida, any doubt? You all have done?
Yes, sir.
Okay. Now, on the basis of this degree of freedom, we may define a specific gas ratio denoted by gamma, which is equals to Cp by Cv. I will define you later what do you mean by Cp and Cv. C is specific heat constant and P is for constant pressure and V is for constant volume. So you may say this is molar specific constant at constant pressure and the denominator part molar specific constant at constant volume. So it will be equals to 1 plus 2 by F, where F is degree of freedom. So if you put the value of degree of freedom for monoatomic, diatomic, triatomic, gamma for monoatomic, it will be 1 plus 2 by 3. So 3 plus 2, 5 by 3. So it will be 1.67. In case of diatomic, it will be 1 plus 2 by 5 or 7 by 5. So it will be 1.4. And in case of triatomic, it will be 1 plus 2 by 6 or 1 plus 1 by 3. That will be 4 by 3, 1.33. Now just compare degree of specific gas ratio for all these three different cases. So you'll observe it will be maximum for monoatomic and minimum for triatomic. Atif, is it clear?
Yes.
And all are greater than 1, but will be less than 2. So gamma for mono will be maximum, then diatomic, then triatomic, but it will be less than 2 and always greater than 1. So range of gamma will be between these two parts. Next, you'll be asked how will degree of freedom will change on changing temperature, or will there be any effect on degree of freedom on changing temperature? You'll say yes, except monatomic. If you increase the temperature of gas, it will tend to weakening the bond of molecule. So it will have additional vibrational energy in it. So degree of freedom increases. So you'll say on increasing temperature, degree of freedom of molecule increases. Riba, is it clear?
Yeah.
So on increasing temperature, bond get weakened. So vibrational energy of molecule increases. Hence, degree of freedom increases. Yusuf, any doubt?
No, sir.
Okay, just write it down. Nara, any doubt?
No, sir.
Okay. Yusuf, done?
Last point, sir. Done, sir.
Next is, what do you mean by real gas and ideal gas? Suppose we may differentiate a gas into two parts, real gas and ideal gas. Riba, do you have any idea what is the main difference between these two parts? The gas which obeys ideal gas equation are called ideal gas, and the gas which do not obey are called real gas. Is it correct?
Yes, sir.
Okay. Let me define you its actual difference. Suppose in a gaseous molecule, if there is interaction between particle of gas, if there is interaction, force of attraction between particle of gas, it will have some potential energy due to interaction between them. And also it will have kinetic energy due to temperature. So on adding these two terms, you will get total energy. In this case of gas, it will be termed as internal energy, denoted by U. So it will be sum of potential and kinetic. But in case of ideal gas, there will be no interaction between particles. There is no interaction between particle of gas. So potential energy in this case will be zero, and only it will have kinetic energy due to temperature. So in total, internal energy will depend only on kinetic energy, or temperature. Is it clear? Atif, any doubt?
No.
So from this, we may conclude a gas which have energy or internal energy, both due to interaction as well as temperature, are called real gas. Another one, a gas which having internal energy only due to its temperature, since there will be no interaction between particle of gas, so it will be called as ideal gas. Now the next question is, how real gas will tend to behave as ideal gas? Let me define you. Suppose you have a vessel enclosing some particle which may vibrate in all directions since all are in gravity-free space. So there will be particle at this point, this point, this point, this point, and this point. So if you exert pressure or if you increase pressure, will the separation of particle increases or decreases? If you increase pressure or if you move this piston towards downward direction, so will the separation between particle increases or decreases? Riva, I'm unable to hear you. Okay, no problem. So on increasing pressure, separation between particle decreases. So in opposite of it, you will say on decreasing pressure, separation between particle increases. Is it clear? Yusuf?
Yes,
Yes,
sir.
sir.
Okay. So first, if you have to decrease the interaction or force of attraction between particle, you must need low pressure, or pressure may be decreased in that case. Next part, if you increase the temperature of that particular system, so particle may vibrate in random direction, so it will have lesser interaction between them in that case. So in conclusion, we can say at low pressure and high temperature, real gas will tend to behave as ideal gas. Is it clear?
I can explain once.
Okay. Since initially, suppose we have particle at this much separation. So if you increase the pressure by moving this piston towards downward direction, separation between a particle decreases. It will tend to collide or to get closer to one another. So on increasing pressure, separation between particle decreases. So interaction between them increases, since force of attraction will be inversely proportional to their separation according to gravitational force, electrostatic force. Okay. So if you need to, there will be no interaction between particle. So you must need low pressure first. Next, if you increase the temperature of this particular system, it will have thermal kinetic energy. The more thermal kinetic energy, it will tend to vibrate more in random direction. In that case, it will have further lesser interaction between them. So we can say at low pressure, it will tend to go far apart between each other. And on increasing temperature, it will tend to go randomly in all different directions. So it will have least interaction between them. So at low pressure and high temperature, real gas will tend to behave as ideal. Is it clear now?
Yes, sir.
Okay. At low pressure and high temperature, real gas will tend to behave as ideal. Okay, just write it down. I'm coming just 2 minutes. Okay, you all have done? Next is what do you mean by system and surrounding? Suppose you have a vessel with piston enclosing any gas, and this gas will be under observation to calculate its volume, temperature, internal energy, heat, work done, or various physical quantity. So this is called system. So system is gas enclosed in this vessel, which is under observation, is called system. The gas enclosed within the vessel, which is under observation, is called system. Surrounding all the outside factors which may affect by any means this particular system is called surrounding. So all the influencing factor which can affect the system by any means is called surrounding, and system and surrounding combinedly termed as universe. Yusuf, any doubt?
No, sir.
Now, depending upon exchange of heat, exchange of energy or matter, we may divide this system into different parts. So next is types of system. First is called open system. Second, closed. And third, isolated. Open system, a system which may allows exchange of energy as well as matter, which allows exchange of energy and matter both. Closed system, which allows exchange of energy only. There will be no exchange of matter. Isolated system, which restricts any exchange. Nahra, any doubt? Okay, just write it down. Atif, any doubt?
No.
You all have done?
Done, sir.
Yusuf, written?
Sir, writing types of system.
Okay.
Done, sir.
Okay. This is all the introductory part of the chapter. So start with mainly zeroth law. This law defines concept of temperature. So you'll be asked which thermodynamical law will define concept of temperature. So you'll say zeroth law. And since it is defined after first law and all the exchange of heat will be responsible on the basis of temperature, so it had to placed before first law, and since there is no natural number before 1, so it will be termed as zeroth, nothing more. Suppose you have a system enclosed by a wall which restricts any exchange of heat, and there is another wall which allows exchange of heat. So this is called adiabatic, which restricts any exchange of heat through it. This is called diathermal wall, which allows exchange of heat through it. So we have temperature or system C, system A, and system B. 3 thermodynamical systems initially at different temperature. So due to their temperature difference, since this thermal wall will allow exchange of heat through it, so there will be exchange of heat through it. There will be exchange of heat through this. this exchange of heat between A and C and this exchange of heat between B and C, it will be till both temperature of A and C becomes equal. And similarly, this exchange of heat between these two systems, B and C, will be up to when temperature of B becomes equals to temperature of C. Is it clear? Suppose we have three thermodynamical systems initially at different temperature. Let's say A at 100 degrees Celsius, B at 80 degrees Celsius, and C at 50 degrees Celsius. So there will be exchange of heat between A and C, and there will be also exchange of heat between B and C. And this exchange of heat will be due to their temperature difference. Up to which part? Till they acquire their equilibrium temperature. And similarly for the case of B and C as well. Is it clear? Atif, any doubt?
Yes, sir.
So we can say in this part, when two thermodynamical system is individually in thermal equilibrium with third system, then they must be in equilibrium with one another. When two thermodynamical system is in thermal equilibrium with third system, then they must be in thermal equilibrium with one another. It means temperature is the physical quantity which defines the exchange of heat between any two different systems. It defines temperature is the physical quantity which defines exchange of heat from higher temperature body to lower till equilibrium. So this part we can say if temperature of A equivalent to temperature of C at thermal equilibrium, temperature of B becomes C, then A and B also in thermal equilibrium with one another. Yusuf, any doubt?
Sir.
Okay. You all have written?
Writing.
There is one announcement. In next class, I will take your Viva. Okay. For that, just revise radiation part from absorptivity, reflectivity, emissivity, transmittance to that Wien's displacement law. Okay.
So
Yes,
which law?
sir.
Yes, Atif.
Which law?
From radiation, from the starting part of radiation, of black body radiation, till Wien's displacement law, the last part of thermal properties of matter. Okay.
Okay, sir.
Yusuf, done?
Yes, sir.
Just
Till
1 minute.
which law? For
Just
the
1
Viva?
minute. Just 1 minute. This is the starting of radiation. Okay.
Yes, sir.
That is from absorptivity, reflectance, transmittance, till the last part of radiation, Newton's law of cooling and Wien's displacement law, this part. There will be only 4 topics: Kirchhoff's law, Stephen's law, Newton's law of cooling, and Wien's displacement law. That's it. Okay.
Okay, sir.
Any more doubt? Umar? Okay. There is an emergency. Okay, so I have to stop here for today. We will continue in next class. Okay.
Okay, sir.
Okay, then we'll continue next class.
Thank you, sir. Good night. Take care.
Thank you. Okay.
Thank you, sir.